So we have seen the application of semaphore, and we find out that semaphore works for n number of processes. It is a software solution, and it is for solving the critical section problem. Now also we have seen some of the application of it, and I have listed here that a semaphore can solve the critical section problem, or it can order the execution of the process, or it is useful for the resource management, right? Now, before going to the rest of the two questions, let's see some more about some more questions related to critical section. So, as in the semaphore, we have two methods, wait and signal. What wait will do? So, this is the code for the wait. Wait is going to see the condition. If condition says that the semaphore value is less than or equal to 0, then the wait will not allow any process to be in the critical section. If s value is greater than 0, then it will reduce the value of s, which is a value of the semaphore, and it will allow any process to go to the critical section, because in the pre-condition wait method has to call. Now what signal will do? In the exit section, whenever a process will execute its critical section, it will come out from the critical section and it will increment the value of s. So there is no condition of incrementing value of s, but here we have a condition to decrease the value of s. What is that? It should not be so s value should not be less than or equal to 0. If it is, then it will go to the loop. This is a busy waiting. That is all busy waiting. Means a process, if semaphore value is less than 0, then a process has to wait for a period of time, because this while loop is making it busy. Okay. And if the condition doesn't satisfy, then while loop will allow it to go out of that and go into the critical section. So that was the logic behind the semaphore, and that is the logic behind the critical section problem. Now, here generally for the critical section problem, we generally use the value of s as 1, or we'll initialize the value of s or value of the semaphore as 1. And because we want that in the critical section only one process can go, that's why we use s value as 1. Let's see the significance of the value of s with the help of one example, where we'll see that when we allow a process, when we allow more than one process to go to the critical section, then what will happen? And when we doesn't allow more than one process, means we allow only one process to be in the critical section, then what will happen? So let's see one example. This is again gate question. It came in 2013 gate, and the question was very big. I make it short, and I prepare the question accordingly. The question says that in the system you have 4 processes, W, X, Y, and Z. These are the 4 processes you have. Here there is a shared variable X, which is a small x, and this is initialized with 0. This is a shared variable. Shared variable means shared resources. Okay, means W, X, Y, and Z. All these processes has a shared value X. It means that they have some critical section, and in this critical section they are updating the value of X, or they are what they are doing, they are writing something on value of X. Now here it says that X is a shared variable. Total 4 processes, that is W, X, Y, Z, are there. And what they do the following thing. So what W will do? W will increment the value of X by 1. This is what W will do. Means W will read the value from the system, it will increment the value of the x by 1, and it will write back the value of x to the system. What X process is doing, it is reading the value of X from the system. It is also incrementing by 1 the value of X, and again it is writing the value to the system. Now what Y is doing? So Y is reading the value of X from the system, decrementing a value of X by 2, and writing the updated value to the system. And what Z is doing? Now Z is also reading the value of X, decrementing the value of X by 2, and writing the value of X into the system, right? Because we are using semaphore, so we have to use these two methods, which is a wait and the signal. So I'm writing the wait method and the signal method in every processes, because it is a critical section, right? Because we are reading the value of X, we are updating it, we are writing it, and we are playing with the value of X. So that particular portion which I have written in the blue color is a critical section. Wait is an entry section and signal is an exit section. Okay, so I think you understood the problem. Now let's see what it is asked. It is given us. So it is given the value of S. It should initialize by 2, means the initial value of S or the initial value of semaphore is 2 here. So the initial value of S is 2 here. Now the question is, what is the maximum value of X after all processes executes? Now this is the question. What is the question? Question says that what is the maximum value of X after all processes execute? Now the options are, the value of X may be -2, the value of X may be -1, the value of X may be 1, or value of X will be 2. So what is the maximum value of X when we execute all the processes? So we have how many processes? We have 4 processes here. Okay. Now let's see the significance of S. Okay. Now what happened when we assume that the value of S is 1? If we'll assume that the value of S is 1, then what will happen? When we assume that the value of S is 1, so if we execute any of the process, let's say we'll execute process X first. If we'll execute process X first, process X will call the wait function. Wait function will see the value of X is more than 1 or not. If it is not more than 1, it will go to the busy waiting, or it will be in the loop. If it is more than, if it is more than 0, then it will go to the critical section. So S value is more than 0, it will go to the critical section by reducing the value of S by 1. Now it will go to the critical section, it will read the value of X. What is the value of X? Initial value of X is 0. And then X will be incremented by 1. So it will be 1. And it will be written back into the system, and then signal will be called. So once the signal will be called, it will increment the value of S by 1, right? This is what happened when we execute one process. Let's assume that we have the value of S is 1, right? Initially, and we are executing one process. Let's assume that we are executing process X. Now, when we execute process S, the wait will be called. Wait will allow this process to go to the critical section because the value of S is greater than 0. And what S wait will do is, it will decrement the value of 1, the value of S to by 1, it is 0. Now it will read the value. So what is the value of X? X is 0 will be read by the X process. Now let's assume that here at that particular point, we got context switch. Context switch means this process will be forcefully deallocated the CPU. It means that inside the critical section, you have a process X. Here, now what we'll do is we are doing context switching, and the control will go to any of the other process. Let's say it goes to Y, and Y want to execute the critical section. So it will go for the wait. What is the wait? S. So wait 0 will be there because the S value is 0. If the S value is 0, so can we allow it go to the critical section? We'll do not allow, because the wait function says that if the S value is less than or equal to 0, it will be in a busy wait. Because it is a 0 value, will not allow Y to go to the critical section. So here mutual exclusion exists, because in the critical section, if one process is there, we do not allow other process to execute its critical section. So mutual exclusion exists, right? As well as progress is also exist. Why progress exists? Once X will perform its execution, means X will do its critical section. So what is the value of S? Value of S again will become 1. Why? Because signal will be called. And at that particular time, because X value will be also incremented, at that particular time, any other process who are interested can go into the critical section. So there is no restriction of that. So progress exists. And we have seen that bounded wait doesn't have any bounded wait phenomena here, because we doesn't have any other variable to find out that some process are waiting for a longer period of time. Now, this is what happened when we see the semaphore with the help of wait and signal method, and will initialize the value of S, or value of semaphore, as 1. Now in this question, the value is initialized by 2. Okay, this is, in this question, it is a trick. That value of S is initialized by 2. So we'll initialize the value of S by 2. Okay. Now we'll try to solve the problem. The problem says that, what it says, the problem says that you have to find out the maximum value of X when we'll execute all the processes. It means that value of X is initialized with 0. So I will execute the processes in such a way so that I'll get the maximum value of X. Now, how it is possible? It is possible if you'll see the processes. We have one process which is incrementing the value, X value, by 1. We have another process which will do the same. But we have 2 more processes which are decrementing the value of X. Here in these 2 processes, they are decrementing the value of X. So can we do something so that Y and Z do not execute? Only W and X will execute. Now in that particular case, Y and Z will not be allowed to execute. But the question says that you have to find the value of X by executing all the processes, right? So can we do something so that we nullify the effect of Y and Z? Even though we are executing, but we nullify the effect of Y and Z. So let's see and find out the trick how we can solve this particular problem. Now in this particular problem, let's say we'll start our process, or we'll start our execution with W. Okay, with W process. Now what is W? W will go to the waiting first, or it will call the waiting. Once it will call the waiting, the value of S will go along with the wait. And because the value of S is greater than 0, will allow W to go to the critical section by reducing the value of S by 1. So what is the value right now? Is 1. Now what W will do? W will read the value of X. So W is reading the value of X by 0, right? From the system. So this is the this is the value of X on W. Now this is the X value of the system. This is the X value of the system. Okay. And now W has, because X is a shared variable, so all are same, right? These two are the same. Now W has read the value of X as 0. Now after that, let's assume that here at that particular point, W will be preempted. Now what is the meaning of preemption? Means W is in the critical section, but we have preempted the W and will try to execute other process. Can we do that? Let's see. Let's assume that Y has showing its interest to execute. So Y, once Y will come, it will execute the wait S. What is the value of S? S is right now 1. So can we allow Y to go to the critical section? Yes, we can allow. Why? The value of S is 1 here. It is greater than 0. It will not go to the loop. Instead, it will decrement the value of S by 1. It means the value of S will become 0. And after that, it will go to the critical section. And what is the critical section? The first step of the critical section is read X. What it will read? Y is going to read X as 0. Yes. Now after that, what Y will do? Y will decrement the value of X by 2. So it will decrement the value of X by 2. Here, it will do it locally first. And then it will write it. So once it will write it, it will go to the system and it will update into the system. So right now in the updated system value of X is -2. And then after that, there is a signal. So what signal will do? Signal will increment the value of S by 1. So what it will do is, here the value of S. So I'll just remove X from here and I'll put it somewhere else. So now this value of S, because signal has been called, the value of S will become 1. Now once the signal of S will become 1, can other process will execute? Yes, other process will also execute. Let's assume that Z is interested. Now once Z will go, there is a wait S. Can we allow Z to go to the critical section? Yes, we can allow, because the S value is greater than 0. S value is right now 1. So we'll decrement the value of S by 1, that is the S value will become 0. And then we'll read X. So it will read the value from the system. So what it will read? It will read X as -2, because the X is -2 here in the system. Now it will decrement the value of X by -2. So it will become -4. And after that, it will do the write operation on the system. And then signal. Once the signal will be called, the value of S will be incremented by 1. Now at that particular time, which process has been executed? So here, process Y and Z has been executed. Process W is executing it. In between, process Y and Z is preempted W. And right now, let's say W want to resume its execution. So what W will do is, W will resume its execution, and it has preempted, or the context switching has done on W at Rx. So because Rx has already been performed here, it will perform the next instruction, which is X equal to X plus 1. So what is the meaning of that? It will increment the value of X by 1, right? and then it will do the write operation, write x. So whatever the value of x, it will write into x, right? And then it will do a signal. Okay, so here it will do the signal, and once the signal will be done, the value of s will be incremented by 1. It will be 2. Now, which process is left? So process x is left. Now x will execute its execution. It will first execute the wait method. Wait, the value of s is 2. So we'll allow x to go to the critical section by decrementing the value of s by 1. And then it will read the value of x from the system. Value of x is 1 right now. So it will read x as 1. And then it will increment the value of x by 1. It will become 2. And then it will write that value to the system. It will write that value to the system. And then there is signal, means it will increment the value of s by 1 again. Right? So right now at that particular state, all the process has been executed. And what is the value of x? So the value of x is 2. So you see here, what is the maximum value of x is possible here? Maximum value of x is possible if we will not allow y and z to execute. The x value initially is 0. It will increment by 1. It will become 1. It will increment by 1. It will become 2. So the maximum value of x will become 2, and we are getting the maximum value of x by 2. So what is the maximum value of x by 2 when we'll execute all the processes? It is 2. So 2 is the right answer. Right? Now, also there may be the question like, what is the minimum value of x? What is the minimum value of x? Can it will be -4, or it will be -2, or it will be 0, or it will be 2? What is the maximum value of x? Sorry, what is the minimum value of x? Now, if we have another question like this, then how we can solve it? So if you understood this, you can understand the second one also. Now, in the second time, what we want the minimum value of x. So if, let's assume that we'll initialize x as 0, so what we'll do so that we'll get the minimum value, because y and z are minimizing the value of x. Maximum value of x would be minimized here is x will become -2 here, and x will become -4 here when we'll execute y and z, and when we nullify the execution of w and x. So once we nullify the execution of w and x, and when I allow the process of y and z, so our minimum value will become -4, right? So what is the maximum value of x that is possible? Maximum value of x that is possible as 2, and minimum value of x that is possible as -4 when the initial value of x is 0, right? With this particular method. Now what we have understood here is, to find out the minimum value of x, what is required? We require that the w and x should not execute. So we'll do the same trick and we'll try to do that. So let's assume that we are executing the process y. So what is the value of s? S value as, we'll take the value of s here. What is the value of s? S value is 2. It will do wait. Y will be allowed into the critical section because s value is greater than 0. It will decrement the value of s by 1, and it will allow into the critical section. It will read the value of x. What is the value of x? X is 0. It will decrement the value of x by 2. So it will become -2, and it will write this particular value into x. Right? That is the process of y. Now what will happen is, we'll not do the updation. Instead, we'll just read the value of x here, and then at that particular point, we'll just do preemption. Once we do the preemption, it means that right now, which is in the critical section? So right now, y is actually in the critical section. So this is the critical section part, right? So y is in the critical section. Can we allow other process to go to the critical section? Here in this case, we'll allow. Why? Because the S value is 2. If the S value is 1, only one process can go to the critical section. So because the S value is 1 here, so right now it is 1 here. So can we allow W? Yes, we can allow W. So if we'll allow W, what is the value of X? X value is S value is 1. So we'll allow 1, weight 1, and because S value is greater than 0, we'll make it reduce to 1, and we'll allow this process to go to the critical section. It will read the value of X and it is 0. It will increment the value of X by 1, and it will write that particular value to the system, and it will make it signal. Once it will make it signal, this 0 will become 1. Can we allow another process? Yes, we can allow other process. Let's say the process is X. Because the S value is 1, X will be allowed into the critical section, and it will read the value of X. The value of X is 1 here in the system, and it will incrementing the value of X by 1, so it will be 2, and 2 will be written back into the system, and it will become this. So it will become 0 first, and now it will become a signal, so it will become 1. Once we got the signal, W and X has been executed. Can we allow other process? Yes, we can allow Y to execute. So let's say when we'll execute when we allow Y to execute, Y has context switching at that particular place. Y is decrementing the value of 2, value of X by 2, it will become -2. -2 will be written back into the system. It will become -2, and the signal will be there. So S will become S will become 2. Now, can we allow other process? Yes, we can allow. We can allow Z to go to the critical section. Because the S value is greater than 0, we'll allow it by decrementing the value of S by 1. We'll read the value of X from the system. It will be -2. Decrement the value of X by 2. It will become -4. And -4 will be written back into the system. And the signal will be called. Then it will become 2. So we have executed all the processes. What is the last value of X? The last value of X is -4. So you can see that what is the answer? Answer is this. Now in this example, you can see that when we have S value is more than 1, we allow more than one process to go to the critical section, and which is a violation of mutual exclusion. Which is a violation of mutual exclusion, and which is a violation of can we say progress? No, progress is not, but mutual exclusion is violated. If mutual exclusion is violated, it is not solving the critical section problem, and it is actually the race condition. What is a race condition? Race condition is 2 or more processes are executing into the critical section. That's why you are getting different values of X. In one execution, you are getting value of X as 2. Another execution, you are getting the value of S as -4. If you will do another type of execution, you might get other value of X. So here, your system will be in an inconsistent state, and this is the classic example of race condition. So you got the understanding of the importance of the value of S in the critical section. So if we are giving the solution related to the critical section, we have to look the value of S. Value of S should always be initialized by 1 when we want to solve the critical section problem.